last lecture, we have introduced the concept of regression. We have discussed how regression could be useful in interpreting experimental data. Regression can build models. It can find parameters of a model, both of which are very important in actual engineering practice. Now we'll take a look at a simple case of regression where there will be one independent variable, one dependent variable, and they are connected through a linear relationship. Such models are called simple linear regressions. In this lecture, we'll look at the mathematical theory of simple linear regressions, and in subsequent lectures, we'll see an example of such regression. Let us take a data set that contains discrete data points xi, yi, where I goes from 1 to n. What we want to do is, given certain input x star, our goal is to find y star, in fact y star hat, which says that this is an estimation of y star or prediction of y star. This is not an exact value of y. The data set here, every xi is connected to one of and only one yi here. That means this xi, yi are ordered pair. x1 and y1 are connected, x2 and y2 are connected, etc. The problem that what we have just described, that comes under the family of supervised machine learning problem. In machine learning, the goal is to learn from data, and exactly the same thing we are going to do here. We will learn from this given data, xi, yi, I equals 1 to n. In machine learning jargon, we call that a training data. It is going to train a model, and that model will estimate this y star hat for us. This x variable is called regressor, or it is sometimes called feature. Y variable is called response, or it is sometimes called label. Every x has given a label, that is the corresponding y. Now think about that we do have a mechanistic model between x and y, where y can be written as some function of x. Now if we have that, then all this question of taking this data, etc., and training the model, etc., not necessary at all. In fact, this entire data set will be completely unnecessary, and we can simply plug in the value of x star here, and immediately we can get an exact value y star. The problem occurs, of course, when we do not have such model. Instead, we have a data set. Then first we have to take an idea, take a guess. It may be from some physical information, maybe that how it looks like. And in this case, we are talking about the situation where this data set looks like that it is linear. That means x and y are linearly related. If it looks like that, then we can think like that this y and x, they are related by a relationship y equals theta naught plus theta 1 multiplied by x plus epsilon. Here theta naught and theta 1 are certain parameters, so we take them as constant. Y equals theta naught plus theta 1x gives the linear model, and this epsilon is the zero mean random error that is inherent in any experiment. The experimentalists do not have control over all the errors. If the errors are systemic, such as there is a problem in the instrument, for example, then the experimentalist can take care of that. But this is not like that. This error epsilon is uncontrollable. It is beyond the scope of the experimentalist. It is given by many different independent phenomena. Epsilon is not only zero mean random error, it is also independent of x. The discussion of nature of this error is more of part of statistics. We will not go detail into this. What we are going to do is that, just like in our previous discussion, we have seen that there is no way we can accurately find the value of theta naught and theta 1. So what we are going to do here, we'll estimate the value of this theta naught and theta 1 by fitting a model that will give us this y equals w naught plus w1x plus e, and this e we'll call that is residual. This is not same as this experimental error. As much as this w naught and w1 are not same as theta naught and theta 1, w naught, w1 are certain estimation of theta naught and theta 1. Depending on the nature of regression, depending on the quality of data set, the w naught, w1 may come close to theta naught, theta 1 or may be far. Similarly, this residual e, that may resemble like this zero mean random error, but in general it is not so. Its statistical property is also different than epsilon, and this e is completely coming from calculation. This epsilon is an experimental uncertainty. So now let us see, the problem at our hand is to find y star for a given x star with the help of this regression model. Y hat is w naught plus w1 x, and this y hat is something we call least square estimation. What is this least square estimation? We don't know yet, and we'll quickly see that. Similarly, this w naught and w1, they are also the least square estimation of theta naught and theta 1, and we'll quickly see that what does this least square estimation means. In the model, this w naught is called bias and w1 is called weight. If I increase the value of w1, the value of y hat will be more dependent on x. Similarly, if I increase the value of w naught, the value of y hat will be less dependent on x comparatively. Now to find this value of w naught and w1, what we do is we minimize cost function, and cost function is defined as the average of loss function, and loss function is defined as the square of this e, that is the residual. For every data point there is an e. I square it up and I add them, I divide by n. This gives me my cost function. This type of cost function has several advantages, but one advantage we can quickly see here, that when I square this ei, then I am taking the magnitude only, and the good thing about it is that ei can be positive or negative sometimes. If I take the li as summation of ei, then li may go 0 and cost function may go 0. But since I am taking ei squared here, that will never happen. That is one advantage. Second advantage is that for such a function, you can see that it will always be continuous. It will always be differentiable. So that is be another good thing, because we are going to differentiate this function very quickly. You will see that. So e, this cost function, can be written as 1 by n y minus y hat. So for the data set 1, y1 minus y hat is w naught w1 x1 whole square. Then the second term y2 minus w naught w1 x2 whole square, etc., all the way up to n. Now we want to minimize this e, and you can see that e has two independent variables, w naught and w1. We have to remember that this x is not an independent variable for the case of e here. E depends only on w naught and w1. Depending on the value of w naught and w1, we will get different values of e. x1 and y1 are known data point. We cannot change that. N also the number of data point. We cannot change that. This value of E in this expression, I can vary only by varying W0 and W1. W0 and W1 is in my hand. So E essentially depends on W0 and W1. And with respect to these two variables W0 and W1, if I take the gradient of E and make it 0, then we get the minimization condition. So when I enforce this, I have to enforce del E del W0 equals 0 and del E del W1 equals 0. It will give me two equations. If I solve these two equations, I'll get the value of W0 and W1. At the same time, this gradient 0 does not necessarily mean that E will be minimum at that point. It could be maximum. It could be a saddle point as well. So to ensure that it is in fact minimum, what we do is that we also verify this del 2E del W0 2 multiplied by del 2E del W1 2 minus del 2E del W0 del W1 whole square should be greater than 0 and del 2E del W0 2 greater than 0. When these two conditions are satisfied, then only along with this together we can say that at that particular point this function is minimum. All right. So let us first try to enforce this condition del E del W0 and del E del W1 to be 0 and try to find out the expression for W0 and W1. Now I have this expression of E. If I take the derivative with respect to W0, you see that each of this term is a square y1 minus W0 minus W1 x1 whole square, etc. When I take the derivative, all these square terms will come as 2 multiplied by whatever there in the first bracket. And then I take the derivative of this minus W0, which will give me minus 1. So then minus 2 will come in front of each of these first bracket together. I sum them up, I get this derivative, which tells me that minus 2 I can take outside by n, and within this third bracket I'll have all these first brackets there, only the squares are removed. So essentially it comes minus 2 by n, y1 minus W0 minus W1 x1, y2 minus W0 minus W1 x2, etc., all the way up to n. So I can write it as a summation, that is minus 2 by n, sum of I equals 1 to n, yi minus W0 minus W1 xi. And then minus 2 by n, summation of yi, I am breaking each of this term, minus n into W0, because W0 will come out of the summation sign, so it will give me n. Similarly here W1 will come out of the summation sign, so it will give me summation of xi. Now what I can do is that this summation of xi and summation of yi I can define on the basis of this average x, x bar, average y, y bar. Average x will be given by summation of all x's divided by number of x, that is n, and similarly average of y bar, average of y divided by n will give me y bar. So I can write here taking this negative 1 minus n inside, because this negative sign I am removing here. So this n W0 becomes positive, multiplied by n it goes only W0. Then 1 upon n summation xi, it gives me x bar, so it comes W1 x bar, minus 1 upon n summation yi, that gives me y bar. Similarly here del E del W1. So if I look at this expression of E here, once again when I take the derivative, every term will have 2 times whatever there in the first bracket. and then the derivative of negative w1 x1, that should give negative x1, etc. Which means that if I take this minus 2 outside, what I'll get is x1 multiplied by whatever there in the first bracket, this term y1 minus w0 minus w1 x1 plus x2, corresponding term in the first bracket, etc., up to xn, corresponding term in the first bracket. So I can write it as the summation of xi multiplied by yi minus w0 minus w1 x1, and now I can break each of this term. What I get is minus 2 by n summation of xi yi. Here again w0 can come out of the summation sign, and I have I goes from 1 to n xi, w1 comes out and it becomes within summation sign xi square. So just like we were writing here as average, we can write here as 2 this w0 x bar, because 1 by n summation of xi will give me x bar. So w0 x bar, similarly w1 x square bar. So here x square bar is not x bar whole square. These are all the xi's are square and then they are added, then divided by n. And finally this xi yi summation of that divided by n will give me xy bar. That is average xy. So these are the 4 averages we have described now, x bar and y bar, and then x square bar, which is different from x bar whole square. It is 1 by n summation xi square, and xy bar, it is different than x bar y bar. Xy bar is 1 by n summation of xi yi. And I have these 2 equations here. You can see that 2 equations contain 2 unknowns, w0, w1. So we should be able to solve them from these 2 equations. Such equations which gives us the regression coefficient, in this case w0 and w1, we name them as normal equations. Now solving this equation is easy. So for instance, I can take this top equation, I multiply it with x bar, and I get w0 x bar plus w1 x bar whole square, this is not x square bar, equals x bar y bar. And then these 2 equations I can subtract one from the other, and I can get this w1 x square bar minus x bar whole square. W0 x bar cancels out. Right hand side is xy bar minus x bar y bar. And then I can write w1 equals xy bar minus x bar y bar divided by x square bar minus x bar whole square. W0 of course is easy to find once we get w1, because it will come from this equation that w0 is y bar minus x into w1. W1 I have this expression. Together now I have the values of w0 and w1. These are my regression coefficient, and now I have the regression model y hat is equal to w0 plus w1x. Now consider this red dot are coming from my experiments, so they are essentially my training data. If these are my training data, I am using those data to get the values of w0 and w1, and then I am plotting this blue straight line, that is y hat equals w0 plus w1x. In this hypothetical case, you can see that none of these red dots are passing through this blue line, which means my regression model doesn't match with any of the data exactly, and yet it more or less shows a very similar trend. Now this is of course a completely qualitative description. What do I mean by similar trend? And we have to give some quantitative reasoning behind that, and we'll discuss that later on. But right now, what we just did, we formalize it as simple linear regression. So what is simple linear regression? Well, it has three properties. One is that it has to be linear, means the y and x, or you can say y hat and x, must be linearly related. There can be only one x and only one y. So one independent, one dependent variable, and there must be a linear relation between them. This kind of regression models are known as simple linear regression. And now that we have our regression model, you remember that getting the regression model is not our goal actually. Our goal was to estimate this value of y star for a given input x star. And now we have our regression model. So I can write this y star hat. That means the estimation of y star is equal to w0 plus w1 x star. And this is where my analysis completes. There are also certain alternative forms of these estimates w0 and w1, and some of these forms are very useful sometimes. So let us see some of these ideas. Here, this w1 is xy bar minus x by y bar divided by x square bar minus x bar whole square. I can plug this expression of averages from here. I plug it in here, and what I get is, this is, first one is 1 upon x, summation of xi yi. Second was 1 upon n. This x bar I am keeping intact, yi. Here 1 upon n, xi square summation and minus x bar whole square. So I remove n from top and bottom. That is why there is an n coming here. And at the top I have xi yi minus x bar yi. So I can write xi minus x bar yi divided by xi square minus nx bar square. So we can work with this particular term here, which is at the bottom of this expression. We define a term sxx is a summation of xi minus x bar whole square. Why we are using it, it will be very clear quickly. I can break this square and I can write this as summation of xi square, then summation of x bar square minus 2 times xi x bar summation. Now here this x bar square can go outside of the summation, so it is n times x bar square. And here also x bar can go outside of summation, so 2 times x bar multiplied by summation xi, and that gives us summation of xi square here, n x bar whole square here, minus 2n x bar square. We are taking it from right here, this x bar. We can see that x bar multiplied by n will be summation of xi. So I am simply using that. So this is 2n x bar square. So now you can see that we can take this out from here and I can write it xi square minus n x bar square, which is exactly the term here. That means I can replace this term with summation of xi minus x bar square. I can write this as sxx, already I have defined, and whatever there at the top, I write that as sxy. Now I am going to do something with this sxy that I have defined. I am going to find an alternative form for sxy. So what I do here is I start from this expression xi minus x bar y bar, which is equal to y bar. I taking y bar out, and I have this xi minus x bar inside. Now summation of xi minus x bar will be 0, because summation of xi I am taking here, I am breaking it, and y bar minus summation of x bar. So summation of xi will come from here, n x bar. This is also n x bar, because x bar can go outside of this summation. So this is 0. So this particular term is 0. Therefore, the Sxy, I have already defined Sxy like this. I can write exactly this term, xi minus x bar yi, and minus xi minus x bar y bar, because this term is 0 anyway. So there is no problem putting it up here. Then this xi minus x bar I can take, and this is xi minus x bar, yi minus y bar, and this is the way I write a new form of Sxy. This forms like Sxx is xi minus x bar whole square, Sxy is xi minus x bar yi minus y bar. These forms are physically meaningful, and sometimes calculation wise, if we take the mean value and we sort of adjust the data corresponding to the mean, then the calculation also becomes much easier. So we'll discuss more about this Sxx and Sxy, why they are making more sense later on. So finally, we have to verify this minimization condition, and my minimization condition is that this del 2e del w not 2 del 2e del w1 2 minus this cross derivative should be greater than 0, and as well as this del 2e del w not 2 should be greater than 0, to ensure that we are actually minimizing this. Now we know the expression of first derivative is like this, that we have already deduced. So I can take the second derivative, for instance here. If I take the second derivative, my del 2e del w2, this negative 2 by n will be here. Then within summation I have minus of w naught, so I have minus of 1. So which gives me this minus cancels, and this summation gives me only n. So this is the value of 2, which tells me that this is actually satisfied. So this is certainly greater than 0. Now I come to this derivative here. This derivative is minus 2 by n. Here I have this w1 xi is here. So I have to take care of that. That gives me minus of xi. Therefore I take the minus sign out. It gives me 2 by n summation of xi square. Therefore, this 2 I already have. I have to find out the cross derivative, and to get the cross derivative in this expression, once again I can take a derivative with respect to w1 here. I get the cross derivative because there is this minus w1 xi here. So I'll get this minus xi here. So it will give me 2 times x bar, because 1 by n summation of xi is x bar. So this is 2 times x bar. So now we have already satisfied this condition. We have to check this condition here. This condition here gives us 4 by n summation of xi square minus 4 x bar whole square, because there is a square here, 2 times x bar, and this gives me 4 by n summation of xi square minus n x bar square. So if you remember that only few minutes ago we have proved that this is equal to this xi minus x bar whole square. So now you see that this xi minus x bar whole square, it cannot be negative, it cannot be 0 as well. If I sum xi minus x bar, that will be 0, but here I have squared them up, therefore it cannot be 0, and certainly it cannot be negative. So this is greater than 0. This expression, of course, I have proved before just a couple of minutes ago. So now you can see that we see the minimization condition is satisfied. More importantly, this minimization condition tells us that this condition is satisfied all throughout in the function. It is not just at the point where this gradients are 0. At every point we have not used the value of W0 and W1, we have deduced by setting this 0. So we can see that no matter what is the value of this W0 and W1 points, at every W0 and W1 points, this minimization condition is satisfied. What does it tell us? So it tells us that every point, this is greater than 0, this is greater than 0. So wherever I'll get this gradient to be 0, that point will be a minimum. And we have seen that when this gradient is 0, we are getting an unique solution of W0 and W1. So there is only one point where this gradient is 0, and definitely at that point the minimization condition, this minimization condition is satisfied. So it tells us that this is the function that has only one zero gradient point or stationary point, and that point is the minima, which tells that this function is a convex function. And this is important, being a convex function, that we have only one minima. We can have only one value of W0 and W1. This has a lot of advantages. This is one of the reasons that why such a function is taken up for regression. So now we are going to summarize what we have learned in this lecture. We have discussed simple linear regression for a training data set T. And by simple linear regression means one regression that is X, one response that is Y variable, and they are related by a linear relation. The regression analysis, what we just did, can be shown schematically like this, that there is an input X and another input is Y. They are coming to this node, and this node is multiplying them with W0 and W1 respectively. Then they are putting them together in this machine where it is being summed up. The output of this machine is my output. This type of visual representation is useful when the model will get more and more complicated. Here we also need to remember this residual E and noise E, they may come close, they may not come close, but they are not the same thing we are talking about. Similarly, theta 0 and theta 1, which we thought that they are the part of the real model, and the regression coefficient W0 and W1, they are close, but they are not same. Theta 0 and theta 1 may be found if I do infinite number of experiments, but we are not doing so. So W0 and W1 is our least square estimate of theta 0 and theta 1. They may be close, but not same. Now for your exercise, you think of fitting a straight line y equals mx through such a data point xi, yi from 1 to n. Use simple linear regression and find the expression of m. Thank you. That's all for this lecture, and I'll see you in next class.